Hello guys, how are you today? So today I'll be explaining AP Chemistry Chapter 4, Shapes of Molecules and Intermolecular Forces. So we start with the very first section, which is section 4.1. It talks about the shapes of molecules and the SEPR theory. It says, how does the localized electron model describe molecules? Very simply, what we should say in this scenario is that the localized electron model, LE, describes a molecule as a substance made up of atoms held together by shared electron pairs, and these electron pairs are either lone pairs or bonded pairs. So if we were to write it, describes a molecule as a substance made out of atoms held together by shared electron pairs, and that's either a bond or a lone pair, so either lone or bonded. Okay, so if you wanted to explain it, you would say that it describes a molecule as a substance made out of atoms held together by shared electron pairs that are either lone pairs or bonded pairs. Now, what does the VSEPR theory state? Very simply, it states three things. The very first thing that the VSEPR theory states is that Coulombic repulsion between electron domains surrounding the central atom determine the shape of a molecule by orienting the electron domains as far apart as possible. So all of this is words. We can very simply summarize. We can say that electron pairs orient themselves as far as possible to reduce repulsion. This is the first thing that it states. The second thing that it states is that non-bonding electron pairs, what does this mean? Lone pairs, basically. Lone pairs repel each other more than a lone pair would repel. A lone pair repels a bonded. Okay, so this is the second thing. And the third and final thing is as well similar to that topic. Lone pairs repel each other more than bonded pairs repel each other. Okay, so lone pairs repel each other more than bonded pairs. Repel each other. Perfect. So these are the three things that the VSEPR theory states. Electron pairs orient themselves as far as possible from each other to reduce repulsion. Lone pairs repel each other more than a lone pair would repel a bonded pair. A lone pair repels each other more than a bonded pair would repel each other. Now, in question 1 part C, they said that they want us to determine the shape and the bond angle. Very simply, we would need to do the Lewis structure. Okay, so the first thing that we will start with is BF3, okay? BF3 molecule, we will start with B, and then we have 1, 2, 3, F surrounding. Now, B is in group 3, okay, that's 3, plus 3 times 7, so that's gonna be 3 times 8, which is 24. Now, what do? We subtract from it 6 electrons. Why? Because we used 3 bonded pairs, so 24 minus 6. Let me just do it quickly on the calculator. That's going to give us an answer of 18. That means we have 18 electrons divided by 2. That means 9 lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Next thing we do is we check if all of the atoms complete an octet. In this scenario, our central atom is boron. Boron is an exception, so boron, beryllium, aluminum are exception. They can be electron deficit. So that means in this scenario, it does not need to complete the octet, whereas everything else completes the octet, so this is perfect. Now, this shape is what? Is AX3. Now, AX3 is what? AX3 is a trigonal planar, if you check the notes on the drawing. And the bond angle of the trigonal planar is 120 degrees, okay? So that is it for the first question. We'll move on to the next question, which is CCl4. We have C and then 4 CLs surrounding it. Now, C is in group 4, right? So that's going to be 4. Plus Cl is in group 7, and that's 4 Cl. So 4 plus 4 times 7, that's going to be 4 times 8, so 32. Now we subtract from it 8 electrons because we have 4 bonded pairs. So we're going to be left with 24 divided by 2. That's going to be 12 lone pairs. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12 lone pairs. Now what do we do in this scenario? We will need to check the and make sure all of the atoms are completing the octet. In this scenario, yes, all of them are completing the octet. And you will look at the shape and you will see that it is what it is, AX4. So AX4 is a tetrahedral shape, right? And tetrahedral has an angle of 109.5 degrees. Perfect. Now we move on to the next one, which is NH3. N, and we have 3 H's. Okay, H does not complete an octet, it completes a duplet. Okay, this is supposed to be a known fact. Okay, so now we start. N is in which group? N is in group 5 plus H, which is in group 1. So that's 3 times 1, which is 3. So in total, it's 8 electrons. And we will subtract from it 6 because we used 3 bonded pairs. So we're going to be left with 2. 2 divided by 2, of course, that's going to be 1 lone pair. And remember, hydrogen never takes a lone pair. That means we will need to put it on our central atom. Now we check, do all of them complete octet and duplet? Yes, they do. Perfect. So this is the final structure. Now what I'm looking at here is what is AX3E. And if you remember, what was the shape of AX3E? It was trigonal pyramidal. So this is trigonal pyramidal. And what's the angle at trigonal pyramidal? It is slightly less than 109.5 degrees. In the answer key, they put the 107. Don't put that because we don't know what the angle is. You just need to say it's slightly less than 109.5 degrees and you will get your answer. Next thing we have is H2O. So H2O, we will draw the Lewis structure. We will have O and then we'll have an H here and another H here, right? So this is what this is. Oxygen in group 6 plus 2 hydrogen in total, that's 8. Minus 4 because we use 2 bonded pairs, so that's 4 divided by 2, so 2 lone pairs. We have 2 lone pairs, okay? So we can't put them on the hydrogen, we'll directly put them on the oxygen. So this looks like what? It looks like AX2E2. And AX2E2 is what? The shape is what? Angular. You can say angular or V-shaped or bent. Either or works. And what's the angle? The angle is also slightly less than 109.5 degrees. So that is it for H2O. We will move on to BeF2. So right? So it's gonna be Be and then F here, right? Now beryllium can be electron deficient. So beryllium is in which group? It's group 2 plus fluorine group 7. So 7 times 2, that's gonna be 7 times 3. So that's going to be what? That's going to be 16, right? We will subtract from it 4 because we used 2 bonded pairs. So that's going to be 12 divided by 2. So 6 lone pairs. 1, 2, 3, 4, 5, 6. And as you can see, beryllium is an exception. So it will not need, right? So basically our structure is what is AX2. And AX2 is what is linear. And its angle is 180 degrees. Now we move on to a bit of a tricky one. I think I'll just move a bit more so I have more space. SCl6. So we will have S over here and then Cl, 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 right? Now S is in which group? S is in group 6 plus Cl is in group 7. How many Cls do we have? We have 6 Cls, okay? So 6 plus 7 times 6, that's going to be 48 minus 12 electrons because we have 6 bonded pairs, so that's going to leave us with 36 divided by 2, that's going to be 18, right? So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So we have 18 lone pairs. Now we need to check if all of them fulfill the octet. Yes, all of them do fulfill the octet. And it's okay for sulfur to have an extended valence shell because it's after period 2. So perfect. That means this is what this is, AX6. And AX6 is what? Where's AX6? AX6 is an octahedral, okay? So octahedral. And what's the angle? The angle is what it is, 90 degrees. Perfect. Now, last and final one is PF5. So we're going to have P and then F, 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 and F. P is in group 5. Plus, how many Fs do we have? Sorry, F is in group 7 times 5. So 5 plus 7 times 5. That's going to be 40. Subtract from it 10 because we have 5 bonded pairs. So that's going to be 30 divided by 2, which is then 15. So now, what do? We will put 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 lone pairs. So basically all of them fulfill the octet. And phosphorus can have an extended valence shell, and this is AX5. And AX5 is what? AX5 is a trigonal bipyramidal. So trigonal bipyramidal. And what are the angles here? The angles here are very simply 120 degrees and 90 degrees, okay? So this is it for this question. Let's move on to question number 2. Carbon monoxide, CO, is produced in the incomplete combustion of gasoline. What's the number of lone pairs on carbon monoxide? Or no, the number of lone pairs on carbon in carbon monoxide. Let's draw the loose structure. Carbon monoxide. Carbon is group 4, oxygen group 6, that's 10, minus 2, 8 divided by 2, that's going to be 4 lone pairs. So we could put it 1, 2, 3, and 4 lone pairs. Now we need to check, do all of them complete the octet? Here oxygen does, but carbon does not, so we cannot proceed like this. We'll erase this, make it a double bond. Still carbon does not, so we cannot proceed like this. We'll erase this and make it a triple bond. And now this is the final structure of carbon monoxide. Now carbon has 1 lone pair, oxygen has 1 lone pair, and we have 3 bonds between them. Question number 3, the following molecule is an amide. Give the values of A and B. Okay, so what we need to do in this scenario is we need to draw the lone pairs, or we need to make sure all of the atoms are in their octet form. Basically, make sure all of them have 8 surrounding electrons, including bonded pairs. So when you do that, you're going to have a structure like this, right? Now we will focus on the central atoms. Over here, this is our carbon, the central atom, and this is our nitrogen, the central, the central atom, okay? So for the carbon, it has 3 bonds, but like 3 surrounding atoms, but it does not have any lone pairs. So we'll say that this is AX3, and AX3 is a trigonal planar, and the angle is 120 degrees. For N, we have 3 surrounding atoms and 1 lone pair, so that's AX3E. AX3 is a trigonal pyramidal, and the angles are slightly less than 109.5 degrees. That's it for question number 3. We'll move on to question number 4. What does it say? It says, draw the complete loose structure for each of the 3 molecules. CCl4. We did them, no? We did CCl4, we did PCl5. We did not do SCl4. Let us draw SCl4. So we have S, Cl, Cl, Cl. Now, S is in which group? It is in group 6 plus 4 times 7. How much is that going to be? 34. So 34 minus 8, because we have 4 lone pairs, that's going to be 26. 26 divided by 2, that's going to be 13. So let's put the lone pairs. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. We will put it on the central atom. Why? It's okay for it to have an extended valence shell because it's after period 2. As long as it's after period 2, it's okay for it to have an extended valence shell. So that's why we put it in the central atom. Now, part B, on basis of loose structure drawn, what's the geometric shape formed by SCl4? SCl4 is what? SCl4 is AX4E. And what's the structure of AX4E? AX4E is a seesaw, right? A seesaw. Is there another name for it? No, only a seesaw. They want us to know that it's a seesaw, and that's it. Now, for part C, 2 loose structures can be drawn for OPCl3 molecule as shown below. Now, they're telling us how many sigma bonds and pi bonds are there in structure 1. In structure 1, we have 1 sigma, 1 sigma, 1 sigma, 1 sigma, and 1 pi. So in total, we have 4 sigma and 1 pi. Now they said, which one of the 2 structures best represents a molecule of OPCl3? Justify your answer in terms of formal charge. So structure 1, let's find the formal charge. We will first start with P. It's gonna be 5. You take the group number and you subtract it from the number of surrounding electrons. Of course, this is 1, 2, 3, 4, 5. You don't take them all, you take only half of the bonded pairs. So that's gonna be 5 minus 5, which is how much? Which is 0. Here it's gonna be 7 minus 7, which is also 0. 7 minus 7, also 0. 7 minus 7, also 0. And over here it's gonna be 6 minus 6, which is also 0. So they're all 0 over here. So definitely this is the more stable structure. Over here, if we did it, we would have what? We'd have 0, 0, 0. We'd have 1, and we'd also have actually, I think there's a mistake here. I think they forgot to put the lone pair over here. That's why it was wrong. Okay. Anyways, it's gonna be what's it gonna be? It's gonna be group 6 minus how many is surrounding? 7. So that's gonna be minus 1. So minus 1 plus 1 in total is 0. But as you can see, most of them are 0. The more that are 0, and most importantly, if the central atom is 0, then khalas. That means that this is the one that we are looking for. Now, anyways, we move on to 5. Use the VSEPR theory to predict the shapes of the following. So we did PCl5, if I'm not mistaken. SO2, let us draw it. SO2. S is which group? S is group 6. Plus oxygen, also group 6. So 6 times 3, 18. Minus 4, so that's going to be 14, because we have 2 bonded pairs. Divided by 2. 7. Oh, okay, 7. So 1, 2, 3, my bad, 4, 5, 6, and 7. Now, of course, we need to make sure all of them have, my bad, I lost my words. All of them have the octet complete. So both oxygens do, but sulfur does not. So we will take from any oxygen, any random one, the lone pair, and we'll transform it into a double bond. So this is the first way it could look. Or it could look, of course, because it's a resonating structure, it could even look like this as well, right? So now, of course, what's the shape of this? This shape is AX2E, and AX2E is what? AX2E, it is what? It is angular, bent, or V-shaped, okay? So this is the shape of SO2. So we did this. Let me just take out the ones that we did. Actually, we didn't do them all. Okay, we'll need to do them all. That's fine. I don't think I'll do them all because it's gonna take so much time. So I'm just gonna choose some important ones. Anyways, the rest I'm gonna leave them to you because we came across all of their shapes except these 3. We didn't come across their shapes. So the first one we're dealing with is ClF3. Cl, and then we have 3F, F, right? Cl is group 7 plus F is also group 7. So 3 times 7, that's gonna be 4 times 7, which is 28 if I'm not mistaken. Yes. So we will subtract from it 6, and we're gonna be left with 22. 22 divided by 2, that's gonna be 11 lone pairs. So that's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll have 10 and 11. Now, what's the structure? On the central atom, we have 3 bonds, so that's AX3, E2, because we have 2 lone pairs on on the central atom. So AX3E2, this is what it's T-shaped, all right? And what's the angle of T-shaped? The angle of T-shaped is less than 90 degrees, okay? So we finished from ClF3. I will do IF4 minus. IF4 minus is very simply, let us see. We start with I in the center, and then we have 4F surrounding it. Now I is group 7, F is also group 7, so it's 5 times 7, 35, minus 8, if I'm not mistaken. How much is 35 minus 8? 27. Oh, I forgot something important. Look what they said. They said I have 4 minus. So what do we need to add? We need to add 1 electron. So that's going to be 36 minus 8. That makes much more sense now. 36 minus 8 is 28 divided by 2. That's 14 lone pairs. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So what is this structure? This structure is AX4E2, right? Now, AX4E2, if you look at it, it is what? It is a square planar. Now, the last and final thing I will be doing is IF5, because we didn't come across this shape before. So I is going to be the central atom, and we have, oops, my bad. We have F, 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 and F. So that's basically 6 times 7, because we have 1 central I, that's group 7, and then 5 surrounding F, which are also group 7. So 6 times 7, that's 42, minus 10, because we used 5 lone pairs. So that's going to be 32 divided by 2. That is going to be 16. So that means we have 16 lone pairs. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So what is this shape? This shape is a X5E, and this shape is called a square pyramidal. And yeah, pretty much that's it for question number 5. We'll move on to question number 6. What does it say in question number 6? They said, what type of hybridization exists in the following? So I'm not going to waste my time and draw them. I'm going to leave it for you guys. I'll give you the shapes of each one. CH4 is tetrahedral. BeCl2 is linear. H2O is bent. NH3 is triagonal pyramidal. BF3, it's triangular planar. And then CO is also linear. Now, quite literally from their shapes, you can memorize their angles, right? So tetrahedral is what? 109.5. Linear is 180. Bent is 100 less than 109.5. Trigonal is what? Also less than 109.5. Triangular planar is 120. Linear is also 180 degrees. Oh, and as well, I forgot to mention, we can also use their shapes as well, because let's say this is what? This is AX4. This is AX2. What is H2? H2 is AX2E2. And H3 is AX3E. BF3 is what? BF3 is AX3. Collinear, my bad. CO does not have a specific shape because it's only 2, so we don't really consider it. We're gonna leave it aside. But anyways, based on their shapes, we can determine whether they're SP, SP2, or SP3 hybridized. Always, if it's AX4, AX3E, AX2E2, so 1, 2, 3, they're gonna be what? They're gonna be SP3 hybridized. If they are AX3 or AX2E, so AX3, it's gonna be sp2 hybridized. And if it's basically, what's the last thing we have? If it's AX2 hybridized, then it's what? It's gonna be linear. Literally anything linear, okay? It's gonna be 180 degrees, so it's gonna be what? It's gonna be sp hybridized. That's it for 4.1. We'll move on to 4.2. The table below shows Pauling electronegativity values and P for some elements. Use the given data to predict the type of bond. Oh, perfect. So what did we say? We said that if delta En is larger or equal to 2.0, then it's what? It is ionic. If delta En is in between, oh wait, this delta En here. If it's greater than or equal to 0.4 or less than 2.0, then it's what? It's a polar covalent. If it is what? If delta En is equal to or greater than 0 or less than 0.4, then it's what? It's a non-polar covalent. Okay, so Li and F, it's gonna be 4 minus 1, which is 3. It's definitely greater, so it's what? It's ionic. Al and F, it's 4 minus 1.5, so it's 2.5, which is greater than 2, so it's also ionic. N and F, 4 minus 3, that's 1, so it's what? It is, 1 is in between these, so it's a polar covalent. And then this is what? This is a non-polar covalent because its delta En is 0. We finish from this, we move on to question number 8. Okay, so for HCl and Cl2, there's a different way to state whether it's polar or non-polar. For BeF2, H2S, CHCl3, HClO, we need to see their shapes. Now, for HCl and Cl2, HCl, Cl, single bond, Cl. Now, of course, going from HCl, we need to follow the Fock-Lin-Brish, right? So what we do in this scenario is we compare Cl and H. They're very far from each other. That means their electronegativity difference is so much. So basically, that means the electron is gonna go more towards Cl, and that will cause it to be what? To be polar. Cl, they're both literally the same. They're gonna separate the electron equally. So it's gonna be what? It's gonna be a non-polar, okay? So this is for these two shapes. For the rest of the shapes, we need to discover their like geometrical shapes, right? So basically, after doing it, I'm gonna leave that for you guys. We will get this to be what? We'll get this to be AX2. This is AX2E2. This is AX4, and this is AX2E2. Now, out of these shapes, we need to remember what are the symmetrical ones. We know the symmetrical ones are what? Are AX2, AX3, AX4, AX5, AX6, and AX4E2 and AX2E3. So here we have AX2, AX4, and yeah, that's it. So that means everything else is directly what is directly, sorry, not non-polar, is directly polar, my bad. Everything else is directly polar because they're asymmetrical. Now, for these, we need to see if they have the same atoms everywhere. Here, look what we have. We have Be, F here, and F here. So, the electronegativity of BeF, it's gonna go like this and like this, but because they are symmetrical and they're the same atom, they're gonna cancel each other out. So that's why we will say that this one is what is a non-polar. Over here, if you drew it, it would be C, H, Cl, Cl, Cl. So if you were to draw the electronegativity, it would be here, 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 and here. This is a bit smaller. So basically, as you can see, this is gonna be polar because it's not equal. Not all of them are the same. If they're all the same and it's symmetrical, it's gonna be non-polar. But here, it is symmetrical, but they're different, so we cannot say it's non-polar. It's gonna be what? It's gonna be polar. That's it for question number 8. We'll move on to question number 9. Xenon can react with oxygen and fluorine to form compounds such as XeO3 and XeF4. Draw the complete loose electron dot diagram for each of the following. Basically, I'm gonna leave that for you guys. Okay, it's supposed to look something like this, right? It will look like this. And then here, it looks like this. This is from the answer key. Here, 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 here. Okay, anyways, for XeO3, the shape is what? The shape is AX3E, because we have one lone pair. Here we have two lone pairs, so this is AX4E2. Okay, so AX3 is what? Is a trigonal pyramidal, and AX4E2 is a square planar. Now predict whether these are polar or non-polar. First thing, we need to check if they are symmetrical or not. This is directly not symmetrical, so this is polar. This is symmetrical, yes, so this is not symmetrical, so it's so it's polar. And this is asymmetrical. That means it's non-polar, especially that all of the atoms are what? Are the same. So directly we say that it's what? We directly say that it is what? It is non-polar. Okay, that's it. Question number 9. Let me just check. 10, 11, 12, 13, 14, 15, 16, blah, blah, blah. Oh my goodness, so many. It's okay, we can do it. We can finish it. Okay, question number 10. Compare the strength of intermolecular forces with ionic, covalent, and metallic bonding. Very simply, what you need to know. Intermolecular forces are weaker than ionic, covalent, and metallic bonding. So you just need to say that it is weaker. 11. There are two types of van der Waals forces, ID, and which are basically London dispersion forces, and PD, which are a dipole, and hydrogen is a type of PD force. Now they said match each of the following with one of the van der Waals forces, a force that exists between two polar. If it's polar, directly we say PD. Intermolecular force between hydrogen to highly electronegative, this is directly hydrogen bond. Strongest of them is a hydrogen bond. Okay, it exists between two non-polar molecules. This is what? This is ID. It's instantaneous, and it forms a temporary. This is also ID. We move on to question number 12. Which of the values given below is the enthalpy change of vaporization of liquid, and which is the enthalpy change of decomposition? What did we say? We said enthalpy change of vaporization is used to break the bonds of the intermolecular forces, which are weaker than the intramolecular forces. Because intermolecular forces will change the state, they require not as much energy that is needed to decompose or break down. Because, as we said, intermolecular forces are weaker than ionic, are weaker than covalent, are weaker than metallic, right? So this for sure is going to be the decomposition. And on top, it's going to be what? It's going to be the vaporization. Now, question number 13. State and explain the trend in boiling points going down group 8 or 18 of the periodic table. So as we go down the group, we know that the boiling points of noble gases increases. This is due to mainly the intermolecular forces, because they're going to have more electrons, right? The more electrons we have, the more stronger the intermolecular forces are gonna be. So the more stronger the intermolecular forces are, the greater energy is needed to break them, so the greater the boiling point. Now, if you want to specify what type of intermolecular force, to be more specific, for the noble gases, the only force that acts on them is the London dispersion force, which is what? Which is the instantaneous dipole-induced dipole. Now, this dipole, okay, as we go down the group, the greater the number of electrons, the greater the electron cloud will become, the more easily distortable. If it's more easily distortable, that means the ID forces are stronger. If they're stronger, then the boiling points are going to increase because we need more energy. Anyways, question number 14, what does it say? Below are the boiling points of propane, C3H8, and the two isomers of butane, C4H10. Okay? They said explain the difference in boiling points between each of the following pairs, propane and butane. Butane has a higher boiling point than propane. First of all, we see that they are both what? They are both organic compounds, only consisting of carbon and hydrogen. Due to this, we directly state that they are what? They are nonpolar. Actually, all of them are nonpolar. So if they are nonpolar, what's the only force that's going to be acting on them? The only force acting on them is the London dispersion force, which is what? The ID. Now, butane has what? A greater number of electrons. Due to the greater number of electrons, it will have a larger electron cloud, will make it more easily distortable. If it's more easily distortable or polarizable, the forces of ID are going to be stronger. The stronger they are, the more energy is needed to break them, so it will have a higher boiling point. Now, between 2-methylpropane and butane, for both of them, they are what? They are both non-polar, first of all, and they both have the same number of molecules. You can find out by counting the atoms and the types of elements. It's like completely the same. The only difference is that butane is more linear, okay? What does it mean more linear? It's less branched. It's like it has, in the skeleton chain, in the parent chain, it has a bigger number of carbons. So if this is the scenario, then for sure, it would be what? It would be having more contact points. So if it has more contact points, there will be what? There will be a larger number of dispersion forces that will form between its molecules and will therefore have a higher boiling point. That's it for 14. We'll move on to 15. Okay, 15a. In the H2SE molecule, H single bond Se single bond H bond angle is close to 90 degrees. On the basis of this information, which atomic orbitals of the sp atom are involved in bonding with the H atoms? If it's close to 90 degrees, the first thing we think of is what? Is the three different types of p orbitals, which are what? The x, the y, and the z. How do I draw them? Actually, let me draw it like this. And the z. Now, think of it like with your fingers. Extend your thumb, then extend your finger perpendicular to that, and extend your middle finger also perpendicular to that, like the right-hand rule, right? So this is how the atomic p orbitals are. They're all perpendicular to each other. So the type of bond that you think of is what is a p orbital. Now for part B, the two types of intermolecular forces present in liquid H2SE and liquid water are London and dipole-dipole. Okay, now they want us to explain if it is soluble in water or not. They said compare the strength of the ID forces in liquid to the ID forces in liquid H2SE to the ID forces of those in H2O. Very simply, the electron cloud of H2SE is greater than that of H2O, so thus it's gonna be stronger. Compare the strength of the dipole-dipole forces in H2SE to that of H2O. So basically, Se is less electronegative than oxygen. Due to this, the dipole-dipole forces of H2O are stronger than that of H2SE. Okay? So this is what they wanted us to know. Question 16, the normal boiling point of Br2 liquid is 238 Kelvin, is higher than the normal boiling point of HBr. Account for the difference in normal boiling point based on the type of intermolecular forces in the substances. So, for Br and HBr, Br2 is what? Br2 is non-polar. Okay, so the only intermolecular forces found in Br2 is what is the London dispersion forces. HBr is polar, so the intermolecular forces found between are dipole-dipole and London dispersion forces. Now, they're saying since Br2 is having a higher boiling point than HBr, then that means the London dispersion forces of Br2 must be stronger than both the London dispersion forces and the dipole-dipole forces of HBr. Now, of course, the greater the strength of the dispersion force, okay, this will be due to what? To a larger electron cloud. So the greater the electron cloud, first of all, the more number of electrons, the greater the electron cloud. The greater the electron cloud, the more easily distortable and polarizable it is. The more distortable and polarizable, the stronger the ID forces are. The stronger that the LDF ID forces are, the higher the boiling point. And that's very simply the explanation. We move on to question number 17. They said specify the strongest type of interaction being broken below when the following changes occur. So looking at them all, you see that they are state changes, meaning that they're all gonna be what? Intermolecular forces, except for one of them, which is over here, and we're gonna discuss it later when we reach it, okay? First thing we reach over here is we see this, right? We see hydrogen with oxygen. Hydrogen will do a hydrogen bond with a highly electronegative atom, which is fluorine, oxygen, and nitrogen. When we have oxygen, directly we will think of what? We will think of a hydrogen bond. So the first one is hydrogen bond. Second one, it's non-polar. Directly we say it's non-polar because they're both, it's the bond is shared between the same element. If it's non-polar, then the only thing left is what is ID. This shape is AX2. AX2 is symmetrical and it's non-polar because both of the atoms are Cl, so that means it's what? It's ID. Now HCl is definitely polar, and when it's polar, then it's a PD. KCl is ionic actually. KCl is metal, non-metal, so it's an ionic, right? And then what's left for the last one is a metallic, because it's a metal, it's changing state from a solid to a liquid, so it's the metallic bond being broken. Okay, that's it for 17. We'll move on to 18. What does it say? It says electronegativity values difference, okay, of SN and CLI. Why am I able to talk? Oh my goodness, sorry. Of SN and Cl are 1.8 and 3.0 respectively. Why is SN chloride, SnCl4, considered a molecular compound? Very simply, if you do 3 minus 1.8, you will get 1.2, which is less than 2, so for sure it's not ionic, okay? That means it's definitely for sure what? It's definitely for sure covalent, and when it's covalent, then the only type of compound it will be is a molecular compound. Now, they said draw the Lewis diagram of SnCl4, predict its geometry, and show the diagram using the diagram why it's non-polar. So SN, Cl, 4, Cl, and Cl. Right, let me make it more Cl. There we go. Sn is which group? Sn, let me check. Sn is group 4 plus Cl being group 7. So that's gonna be 4 plus 4 times 7, that's 32. Subtract from it 8. 32 minus 8, that's gonna be 24, divided by 2, that's 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. That's what 12 lone pairs. And now you check it and you see that everything completes the octet, so it's perfect. So what's the shape? The shape is AX4, so it's a tetrahedral, and AX4 tetrahedral is symmetrical. Since it's symmetrical, it's gonna be non-polar because all of the polarizing forces, even though the SnCl is polar, but the whole molecule is non-polar, right? So the whole polarizing force is gonna cancel each other out, and due to this, we say that it is what? It is non-polar. Now identify the type of intermolecular force between S and Cl4. It's non-polar, first of all. So because it's non-polar, we directly say that it's a London dispersion force, ID. So question number 19. The structural formula of 1-aminopropane and propane are shown below. Account for that 1-aminopropane is soluble in water, whereas propane is not. You must discuss both compounds in your answer. So what do we have? First of all, we have 1-aminopropane, propane, and water. We should not forget about that. Now we need to list the forces. 1-aminopropane has what? It has the strongest bond for it. Of course, we'll only consider the strongest bond being the hydrogen bond. It has dipole, it has ID, of course it does. But it has a hydrogen bond. How did we know? Because we have a nitrogen over here, right? And this has a lone pair, right? So this nitrogen is what? Is one of the electronegative, the three of them. Fluorine, oxygen, nitrogen. So what will it do? It will form a hydrogen bond directly. So this is for the aminopropane, so it will dissolve in water because H2O also has a hydrogen bond. Whereas here, this has what? An induced dipole. So for sure, it's not gonna dissolve in the water. Here, same exact thing, but we need to discuss their boiling points. Diethyl ether and butanol. Okay, so this is actually very important. So diethyl ether, as you can see, we will focus on the oxygens. They're very important to us. As you can see, diethyl ether, mainly it's supposed to have ID forces. Why? Because from here and from here, it's symmetrical. When it's symmetrical, that means it's gonna be non-polar. In this scenario, I searched it up and it has a little bit of polarity, but not that strong to be considered polar. So the mean force would be what? It would be considered more non-polar than polar. So the mean force would be the ID. Whatever they said in the answer key is a bit confusing. So it's going to be what? ID. Over here, it is polar. How do we know? Because it's not symmetrical. If it's polar, for sure it can react with the water, right? So it will form a hydrogen bond with the water. So definitely for sure, because it has I was gonna say oxygen, because it has oxygen, right? It will form a hydrogen bond, because fluorine, oxygen, and nitrogen can form a hydrogen bond. So definitely for sure, I think here they also mean butanol. Definitely for sure, butanol will have the higher what's it called, boiling point in between the two. We move on to question 21. What does it say? It said, explain the trend in boiling points from pH 3 to SbH 3. Very simply, all of these, if you drew their structure, you would get what? You would get a non-symmetrical geometrical structure. So that means for sure they're gonna be what? They're gonna be polar. So since they are being polar, the type of force they have is the PD-PD. Now, NH3 is an exception. We don't consider it, but from pH 3 and onwards, it keeps on increasing the boiling point. This is due to the increase in what? The increase in the number of electrons. The greater the electron cloud, the easier it is to distort, and it will increase the strength, right, of the London dispersion force, because don't forget that we also have London dispersion forces as well as the PD-PD. So thus the boiling points are going to increase. Now, ammonia is what? The only exception, okay? However, ammonia molecules, okay, have a hydrogen bond in them. And hydrogen bond is very, very strong, right? We said it's stronger than PD-PD and it's stronger than ID-ID, but it's not stronger than ionic. It's just strong in general, and the intermolecular forces. So due to this, it will have what? It will not have an anomaly, and it will not follow the trend. Now, question number 22. Arrange the following molecules in increasing order of boiling point: HF, HCl, and HBr and HI. So HF, we will exclude it from HCl, HBr, and HI because it forms a hydrogen bond. It will have what? It will have the highest boiling point. Then, after that, we need to talk based on the number of electrons, because whatever else we have left is the PD-PD and ID-ID. For the PD-PD and ID-ID, the greater the number of electrons, the greater the electron cloud, the easier it is to distort, the greater the force needed to break the bond, and then the higher the boiling point. That means that the weakest is HCl, then HBr, then HI, and then HF, okay? So that's it for 22. We'll move on to 23. Name the strongest interactions between the particles. Each of the following. So Cu is definitely for sure a metallic bonding, because it's a metal. CaF2, if you did the electronegativity difference, you're gonna see that it's an ionic. And H3 is a hydrogen bond directly, because you see hydrogen with one of the electronegative atoms. CH3Cl. Okay, here for this one, it's a polar molecule, because if you drew it, you're gonna get it to be a tetrahedral, right? However, not all of the atoms are same. Not all of the atoms are the same. So due to this, you will see that this is what? Polar, so it will be PD-PD, so dipole-dipole. And E, the last one, is H2. It's the electronegativity 0, so it's a non-polar covalent bond, meaning it's what? It's an LDF or ID-ID forces. That's it for 23. We'll move on to 24. Account for each of the following. At 25 degrees in 1 atmosphere, F2 is a gas, whereas I2 is a solid. This is due to what? First of all, we look at them. They are both what? They are both linear. And if they're linear, that means it's a symmetrical shape. If it's a symmetrical shape and both of them have the same element, then it's gonna be what? Then it's gonna be nonpolar. So both of them are nonpolar. We can't say that it has PD-PD. We can't say that it has hydrogen bond. Only thing left for us is the ID-ID. Now, what's the difference in ID-ID? It's the number of electrons. I2 definitely has a greater number of electrons. So due to this greater number of electrons, it will have a stronger ID force, a stronger London dispersion force. Thus, it will become what? It will become a solid. Now, the melting point of MgO is greater than the melting point of CsCl. MgO, ionic, CsCl, ionic. Mg is Mg2 plus, Cl is Cl, O is O2 minus. Cs is Cs plus, and Cl is Cl minus. Now, first thing we do is we compare the size of Mg and Cs. For sure, the atomic radius of Mg is way smaller than the atomic radius of Cs, because Cs is in, I don't know which period, but Mg is in the 3rd period. For sure, right? Now, what makes it even smaller is the fact that it's a 2+. The greater the more electrons we take away, meaning the more positive it becomes, the smaller the atomic radius. So this is already what really small. Now for oxygen, if you compare its size to chlorine, you'll see already that it's smaller than chlorine. But 2-, you're adding 2 electrons, it's gonna be a bit bigger, but it's not gonna be the same size as chlorine. It's still gonna be smaller, so it's gonna be like this, okay? Now, for CS+, we said it's gonna be probably like this, and for Cl-, we said it's probably gonna be like this. So definitely, as you can see, the distance between the nuclei of this one over here is closer than the distance between these nuclei over here. So what does this say over here? This says that the atomic radius of Mg2+ and O2- are smaller. So due to this, the electrons will attract more because the nucleus is closer to the electrons. Whereas between Cs+ and Cl-, it's larger atomic radius, so the electrons are farther apart, so it's going to be harder. So that's why the melting point of MgO is greater than the melting point of CaCl, because MgO has stronger ionic bonds. Now, ammonia is very soluble in water, whereas this is only moderately soluble in water. First of all, ammonia is one of the greatly electronegative, so it will have a hydrogen bond. pH 3 is a polar molecule, so it will have only the PDPD, or like the permanent dipole only. Now, water has what? Water has a hydrogen bond, right? And it also has a PDPD. However, the hydrogen bond is the strongest, so it will definitely be it will definitely make the atom that has a hydrogen bond dissolve, or become more soluble than the one that does not have a hydrogen bond. So very simply, because this has a hydrogen bond and this has a hydrogen bond, it will be very soluble in water, whereas that one is not that soluble in water. Now, Si melts at a higher temperature than I2. So Si is in which group? In group 4. And in group 4 we have carbon, silicon, germanium. All of these form what? All of these form covalent. They're all covalent structures. Whereas I2 over here, this is a covalent structure, but it's what? It's non-polar, so that means the only force it has is IdId. Now, IdId is the weakest force out of all of the forces we've taken so far. So definitely, for sure, covalent is going to have a much higher temperature than IdId. That's it for 4.3. We still have 6 questions for 4.4, and then we're done. Perfect. So give 3 anomalous properties for water. First thing is that solid water, which is ice, is less dense than liquid water. Second thing, water has a strong surface tension. And third thing, that water has a relatively high melting point and a boiling point. 26. Both water and ammonia molecules exhibit hydrogen bonding between their molecules. However, boiling point of water is much higher than boiling point of ammonia. Explain this. Now, this is very simply to do with the Lewis structure. If you draw the Lewis structure of water and the Lewis structure of ammonia, NH3, you will notice that oxygen has 2 lone pairs, whereas ammonia has 1. That means ammonia can form only 1 hydrogen bond, whereas oxygen can form 2. Now, due to this, there's going to be more extensive hydrogen bonding between water molecules, right? And this will lead to the big difference in their boiling points. 27, name this intermolecular interaction between water molecule ions. This is the What? I didn't even read the sentence, my bad. Name the intermolecular interaction between water molecules and ions. Sorry, between water molecules and ions. They missed that one. This is called an ion-dipole interaction. So when you see ion and water, it's called an ion-dipole interaction. 28. The decomposition reaction of NaOCl occurs as shown below. Draw the Lewis structure and dot cross diagram for each of the following. Okay. Let us do an OCl. The most electronegative, which is not oxygen and which is not hydrogen, should be in the center. So in this scenario, it's going to be N, right? So N, and then O, and then Cl. This is how it looks like, right? So then oxygen will have 1, 2, 3, 4, and then it will have 2 inside here. And then nitrogen is gonna have 1, 2, and it's gonna have 3, 4, and then 1 inside of here. And then chlorine is gonna have 1, 2, 3, 4, 5, 6, and 7. So this is what the dot cross diagram of this looks like. If you drew the Lewis structure, it would be like this. It would be N, double bond oxygen, right? And then oxygen has 2 lone pairs. And then single bond chlorine, and chlorine has, I don't know how many lone pairs, 3 lone pairs. And then don't forget the lone pair on nitrogen. And this shape is what? Is AX2E, right? Now, what's the shape of AX2E? It is what? A bent, if I'm not mistaken, let me double check. AX2E is a bent geometry. This is the shape. Now, NO, NO, right? So N is which group? Oh, sorry, we're doing the dot and cross diagram. Nitrogen, oxygen. So nitrogen, let's do the Lewis structure first, actually. Nitrogen is in group 4, nitrogen is group 5, oxygen is group 6, 5 plus 6 is 11, okay? So that's gonna be 11 minus 2, that's gonna be 9. 9 divided by 2, 4.5 lone pair. This 0.5, it's more preferable to put it on the nitrogen. So here it's gonna be what? It's gonna be 1, 2, 3, 4, and then 5. Now, of course, nitrogen doesn't complete the octet. Oh, so actually what I think happens is this goes here and it comes here. So this is what the structure looks like now. So if we were to draw the dot and cross diagram, it would be like this. This is very confusing. Okay, it would be like this. We would have, and then here would be 1, 2, 3, 4, 5, 6, and then here it's 1, 2, 3, 4. Okay, now this one is a weird structure actually, but since it's only 2, because it's only 2 elements, pay attention, only 2 elements, we directly say that it is linear. Now Cl2 is probably the easiest one out of them all. Cl, we have 1, 2, 3, 4, 5, 6, 7, and then here we have 1, 2, 3, 4, 5, 6, and 7. Okay, so this is what it looks like here. Here it's gonna be single bond, like this. And because it's only 2 elements, it's gonna be what? It's gonna be linear. Part B, which bond is expected to be longer? NO or NCl? Explain. Now this depends on the atomic radius. Between oxygen and chlorine, definitely chlorine has a greater atomic radius. So due to the greater atomic radius of chlorine, NCl will have a greater bond length. Fill in the table below with the major intermolecular forces present between the given molecules. So NOCl, it is what? It's not a, I think it was AX2E. So it's not a symmetrical, first of all. Second of all, what do we have? Second of all, we have 2 different elements, right? So in all scenarios, it would be what? It would be a polar molecule, meaning the major force is the PD, dipole. Now, NO is linear, right? But at the same time, because they're 2 different elements, it's gonna be polar as well. So it will also have PD. And then Cl2 as well. It is linear, but both are the same element, so it's gonna be what? London dispersion forces, which are what? Which are ID. Why is NOCl more likely to dissolve in water than Cl2? Because NOCl has PD, which is a stronger force than ID, and water has hydrogen bond, PD, ID. So you see, okay, water has PD, NOCl has PD is stronger than ID, so for sure, NOCl will dissolve in water. And on top of that, the fact that NOCl is polar and Cl2 is non-polar. Okay, we're gonna finish soon. 29 top. Draw full Lewis structure for CBr4, PCl5, SBr4. Okay, I'm gonna leave that for you guys. Now for part II, what is the molecular shape of SBr? I think I'm just gonna draw SBr shape, right? Oh my bad, I forgot BR, CBr. Okay. They told us in CBr4 they want the bond angle. Oh, so in this scenario we'll also need to draw what? We'll also need to draw the CBr4. So actually when you draw it, it's gonna be a tetrahedral, right? So it's gonna be something like this, if I'm not mistaken. So it's a tetrahedral, and the angle in a tetrahedral is what? Is 109.5. Now for SBr4. Alright, let us. So SBr4, we will start with S in the center. We have 4 BRs, BR, 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 BR. But I think when you do it, you're gonna have a lone pair on S. Okay, it doesn't make sense, but we will have a lone pair on S. Due to this, the structure is AX4E, and AX4E structure, what is it called? AX4E, it is called a seesaw structure. So the structure of this is what it is, a seesaw structure. Now part C, 2 possible Lewis structures for phosphate are shown below. How many sigma bonds and pi bonds are shown in diagram 1? In diagram 1, we have 1, 2, 3, and 4 sigma bonds and 1 pi bond. Which diagram is a better representation? So in my opinion, it would be better that always the central atom will have what? Will have a formal charge of 0. So you do all of the formal charges. You're gonna see for the first one, if you do the formal charge of P, it's gonna be what? It's gonna be 0. Of oxygen, it's gonna be what? It's gonna be actually this oxygen over here, it's gonna be 0. And then these 3, it's gonna be what? It's gonna be -1, -1, -1. Right? Whereas if you did for diagram 2, you would have the central atom to be +1. Then this one is how much? This one on top is -1. And then they're all -1. So definitely for sure, it would be better if the central atom is what? The central atom is 0. So this is why we prefer this, and on top of that it has more zeros. So this is why we will prefer diagram 1. That's 29 done. Now 30. Use the principles of atomic structure and bonding to answer the following question. For propane, draw the Lewis structure of propane. Okay, let's draw the Lewis structure of propane. We have C, H, 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 single bond C, double bond O, single bond C, H, 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 and don't forget the free electron pairs or the lone pairs on oxygen. Now part 2, they said predict the carbon-to-carbon bond angle of the central carbon atom. This is the central carbon atom. They want the bond angle. So from this we'll have 1, 2, and 3. It's a carbon central atom with 3 atoms attached to it. So that's gonna be what? It's gonna be AX3. And AX3 is what? It is a, I forgot the name, my bad. It's a trigonal planar, and always in the trigonal planar, the angle is 120 degrees. Now, we move on to part B. It says, given the structural formula of ethene below, indicate the hybridization of carbon atom indicated by the arrow in the structure above. They want the hybridization of carbon atom. This is the carbon atom over here, right? Now, as you can see from this carbon, what does it have? It has here a single atom, and over here it has kind of a single atom as well. So the structure is what? Is AX2, because there's no lone pairs, and AX2 is always what type of hybridization? It's always sp hybridization. Indicate the total number of sigma and pi bond in the molecule. Here we have 1, 2, 3 sigma and 2 pi bonds. Easy peasy. Okay, now the last question. Shukra Allah. Draw the Lewis structure of C2Cl2 molecule. So I'm gonna leave that for you guys, but it's supposed to look something like this. C triple bond C single bond C L. My bad. And then here Cl as well. So this is what it's supposed to look like. They said the carbon to chlorine bond length in C2Cl2 is 177. How will the carbon to bromine bond length compare? So bromine has a larger atomic radius. It has more electrons, so it's going to be greater than 177. Now, the carbon to chlorine bond energy in C2Cl2 is this much. How will the carbon to bromine bond be? It will be less energy, right? Why is this? Because we said it has greater number of carbons, so the atomic radius is bigger. If the atomic radius is bigger, that means the distance between the nucleus of the carbon atom and the bromine valence electrons are larger, okay? And due to this, the attractive forces will decrease, okay, as per Coulomb's law. And due to this, the bond energy is going to decrease because it's going to be easier to break. Or you can remember that the longer the bond, the less the bond energy. Part D, what does it say? Name the intermolecular forces present between the molecules of ethanoic acid and between the molecules of butane. Okay, ethanoic acid. Ethanoic acid has oxygen and it's non-polar, so that means it has hydrogen bond, PD-PD, and what also does it have? ID-ID. Here, this is a hydrocarbon, right? That means it's only carbon and hydrogen. So due to this, it's a non-polar, right? And if it's a non-polar, then the only force that it has is the London dispersion force, which is ID-ID. Now, what did they tell us? They told us that the boiling point of butane is this much, whereas ethanoic acid is this much. Explain. We know that because the boiling of the acid is higher, the boiling point of the acid is higher, then the sum of the intermolecular forces is greater than the sum of intermolecular forces of butane. So the sum of intermolecular forces of ethanoic acid is greater than the sum of intermolecular forces of butane, right? So now this can be explained due to the presence of hydrogen bond and PD-PD, whereas this only has what? ID-ID. So that's it for this video. Thank you guys for watching. I hope you enjoyed and have a wonderful